So the talk I'm going to talk about today topic is about pointwise criteria of p-adic local system. This is joint work with Ziquan Yang. And I would also like to thank Shaka Petro for helping us for collaborating in our early stage. So just as a very first introduction, I'll give some background about the notion that we studied, which some of them has already appeared in the previous talks. Say we have a finite extension of p-adic field. So let's say okay is talking of integers. If okay is a p-adic field. So starting with this data, we can look at the Galois repetition. Whereas B is a finite dimensional vector space or so very important question in p-adic Hot theory is asking, like, what can you say about representation? Or when does it become interesting? So specifically, there's a notion called geometric, which is saying that this representation assures us a certain part of the default homology of some varieties. Question. What is in geometry? So to understand this condition, the Fontaine introduced several pure rings to really make this rigorous. So in particular, we introduced several subcategories of representations like that to capture like the necessary conditions by this thing. Some variants the wrong, the table. All those systems. A subcategory of another category of finite dimensional Galois representations. So those things are kind of and so by many people talking about contributions, so we are nowadays know what kind of situation you get the representation which fall into those subcategories. In the first case, you got Gram representation. So one condition that is sufficient is that is be geometric. So the first condition is not like the geometric condition. So, in particular, if you want the given representation to be geometric, the necessary condition for you will be it has to be developed. And in addition, so what about final motions? The second and third case, and then you can add some more string on this X. And the semi-stable representation will happen if you X as that one, it happens when X has to be count. So those are kind of the fundamental progress in p-adic Hot theory. Many people have contributed to this, including people here. Just to name some of them, like including starting to the domain. So, the argument. and also some written one. I apologize in advance if I didn't make a comprehension, but I usually just mention about. So once you have these notions, and then you somehow have already good understanding about representation. But you can ask, what if you consider a relative notion? This is kind of topic I want to emphasize for the rest of the part. So what does this really mean? The setup here will be you start with a smooth rigid space. And then an extension of p-adic representation in the case of point will just be a local system, so p-adic local system. But just to describe these things and make it slightly precise, I'll look at the link for the PD. So you can think about this as kind of a family or geometric family of p-adic representations. Namely, there should be a certain full system of equal shape over X. In particular, if you restrict this thing to each close point, you get actual Galois representations of the relative. So this is kind of, in particular, this gives you a family of representations. And now, once you have this general setup, and then so you can also ask if you have the notions like the RAM, semi-stable, and crystalline as well. And so this was also kind of extended by partings. And I guess although I mentioned Riemann and that is, there exists such an extension of the RAM table. In the sense that in the case of point, it's really recovered the same definition about. So now you can ask the next questions, and then so do you also have this kind of analogs that people have a geometric family, and then you get the randoms, and if you have a certain geometric family, and it turns out to be even semi-stable, some correct sense, and you get refined notion of local systems. And so this question becomes more technical and harder because you have to formulate this correctly and think about the relative setup and how to make those comparisons. So let me name some progress that we have already seen. Let's use this indicator to that problem. So the first one is about the RAM notion or the RAM local system. So this notion actually has a very complete understanding, or at least the picture about expand completely. So this is, for example, due to the work of Shota. Saying that the map of rigid space. And have a direct image of a constant ecological system is a Riemann local system space. So in particular, you say the first implication extends to a relative setting. So you can ask what about the other terms. So what we know here is that if you assume it's crystalline or the most finest regions here, and then you also get something there. So this is my previous joint work with Riemann Hilbert. Saying that the setup here is slightly different. That turned out to be a map of p-adic formal spins. And you can also assume smooth power. And then when you look at the same thing, like the higher direct image of a system on generic fiber, I'll take us still the same little app. This is different. However, in the setup, the semi-stable document here has not been extended here. Still is well expected. So this is kind of first series of works that I want to mention, which is talking about this implication from geometric content to abstract content. The second point I want to mention is for the ground local system, there is actually something very useful in factors. It's called rigidity. So this is discovered by the work done by Liu and Zhu. So what this really means is that if X is connected, and let's assume the same thing that you have consistent over X. And so if you want to say this local system theorem, it's best to have that one single point. So in particular, this makes the consideration of Pierce problem much simpler, in the sense that like once you look at this local system, the higher direct image, to check these things to be derived, it's suffice to just look at one single fiber and then do the work there. And so this is called the rigidity. So those two are kind of things that we have seen about the local system. And then so there are natural questions you can ask. First one, just like what I mentioned, you don't have. So how do you extend this into a semi-stable case? Second one is that, so do you also have this similar behavior but for other local systems? In the sense that if you pick a favorite local system and you want to check its crystalline, for example, can you just do that by restricting at points? It's a natural question you can ask about extending the second one. So today I want to provide some partial answers to that, and which some of them can be quite useful, I think. The first one, ready to start on right image. On PI and so on. That is, turns out the semi-stable condition in the relative setup also has an analog. So that is if you how we set up that from that. Sorry, all right. Let me just mention directly from this for now. So map of p-adic formal spin right? Condition assumed here is that it's proper. And also the so-called weakly semi-stable. I will comment on this question. Here I also assume and those two thoughts and target are the p-adic formal scheme, which are semi-stable. And then you look at the higher direct image on the generic fiber, a constant normal shape. And what we have here is that this local system is semi-stable. So in particular, so just compare.
What does it mean replacement?
Yeah, I will mention. So if you just look at statement instead of exactly extending the case to a semi-stable situation. And here, the semi-stable, this morphism, semi-stable morphism is kind of, based on what we say, there are no very standard definition of that. And one thing we can do is that here, you talk locally on source and target. You want it to be something like roughly have this kind of formulas, which is in like several variables. And such that you want this condition to be a multiplication of xi is equal to some power of unique matter times the unit. So then you follow the formula. So roughly speaking, if you look at the things when R is just okay, and then you roughly got slightly weaker notion of a semi-stable species. And yeah, I won't say this is only one way of presenting the work, and I just hope to present something simple. You can actually refine us adding more conditions, or sorry, dropping the conditions so that it only happens at this point.
And what does it mean for a local system to be semi-stable?
Yeah, so one way to think about that, thank you for asking. It's really saying that, so if you have a local system and then you also have another act as a crystal over the spiral fiber, which where the spiral fiber is taken to be locked inside. This or you do spiral fiber, or you take certain log structure which is based on the compound you choose. Like if you assume it's smooth and then the log structure you take is just a dermal, and take some big logs. And if it's semi-stable reduction, you have more refined version of that. But roughly speaking, you want to act as a crystal or a special fiber together with the condition that this is comparable to the local system. In the sense that the local system, after change to certain period shapes, for example, the PSP, and then so that is isomorphic to the evaluation of F as a crystal on PSP.
What is BST?
Let me say this, you can do B quiz, which is saying that you take a shape A in and take a P complete divided power along the surjection theta. And then you invert by
This I have no problem. I have problem with BST.
yeah, I would say this is equivalent. Yeah. I can talk about things in more details later. But roughly speaking, like
So a priori this E doesn't have monodromy or anything.
it's kind of encoded by the log structure you have. So that is, it's act as a crystal on the log crystal side, not the crystal side.
And the log structure is kind of funny.
Yeah, the log structure here is coming from because you have in this case, the Buddha reduction case is just corresponding to a new Horton and morphism of F as a crystal. Yeah.
And just to make sure, in the equation defining with some stability, do you need the power of this uniformizer to be R? Which is
You mean this one? R is standing in origin.
They also have R variables. Oh, this is not the same.
Oh, thank you. Thanks for touching on it. This is that's all I have. Of course, it has different. Yeah, any other question?
So a priori, your notion of semi-stability depends on your model.
Thanks. I will mention that very soon. I got a very satisfying answer to this. Oh, at least to me, or to myself. Okay, so any other question before I start to talk about what's really input? So what really make it possible is our probably the central contribution of this project, which I call it theorem 2, which is saying that to test some local system to be crystalline or semi-stable, it actually suffices to just test it at point. So experiment is following. This is log AT in order to handle the local system on that time. And then the claim is that this notion of crystallinity or semi-stability is referring to saying that the restriction of V at each closed point is a crystalline or semi-stable representation in class. So that is like saying like you have a criterion of crystallinity or semi-stability by checking a point.
So closed points mean the points in the classical rigid sets.
Oh yeah, I think in our article we already say it as a classical. Locally
Because fields are finite extensions.
exactly. So that's critical as I will mention very soon. But just for a statement, are there any more questions? Okay, so at least after stating that, I can immediately tell you what goes to the doing the first theorem. It's actually I probably want to probably it's more appropriate to just mention that as a corollary. But I think the comparative theorem is not playing a very important role to me, so I'll make it a theorem. Here is a remark which kind of explaining the relation of those two things. First one is that how do you prove this theorem dark image? These things follow immediately from combining two results. First one is our proof that you can check this condition by restricting at points. The second one is a classical result, which I mentioned in the previous blackboard, that if you restrict to each closed point and you look at such a restriction, And this semi-stable, so in this case, you will get a proper and weakly semi-stable p-adic formal scheme. And this Ziquan homology is actually semi-stable, which I probably can mention that as say CIP conjecture in absolute sense. I guess now this all can say it's a zero in absolute sense. So for this result, like in these specific situations, and I think what we use is this work by Comis and Lido. But this work was clearly also first time, I think, by Suzy. And it's also applicable into make it slightly tricky. And also recently by this navigators. That is because by power base change, when you look at the restriction of the Hilbert image at the close point, you then return or you just reduce to looking at the epochal homology of certain semi-stable or p-adic strictly semi-stable 3D space. And that homology is semi-stable by the most work. So you can see that it's kind of a quick consequence. And the second condition or second remark I want to say here is so this statement serum PC, we also have an p-adic version of that. This and p-adic version of. By which that means that you look at the unramifiedness of an p-adic local system, where L is anything.
That's like an analog of the crystalline statement. Is there also an p-adic analog of the semi-stable version?
I really hope to understand these things, and at this moment I don't have an answer. Yeah. So,
sorry, I guess you should repeat the question.
Oh, sorry. The question is there also a semi-stable analog for p-adic local system? And the answer is no. I don't know. Sorry. Okay, so this is kind of a remark just for those two statements. And as you can see, this theorem, the direct image follows immediately from what people have done before. And you can do slightly more work to show that this local system, which you know that is semi-stable, is also associated to the relative Kriging homology or log Kriging homology of spiral patterns, which is kind of the complete statement for the comparison theorem in the relative science. And I think a very important contribution, at least for me, about this theorem PC or Pointwise criterion is that this allows us to greatly reduce the comparison theorems in the relative setting just to the absolute setting. So if you have read any of those articles, you know they are all very long. And then doing that again for even more complicated setup is just painful. And but nowadays, I actually tell you that you probably don't need to do that. And so to make these things even more, I have some other big applications of this result. The first one is about pullback, which I think also kind of answering the previous question by Paul. So, which is saying that this notion, the crystallinity of semi-stability is kind of preserved under pullback, even if you don't know that the map comes from input of pullback. That is, let's just say you have a map rigid space. And assume let's say you know the source and target has some like good or semi-stable reduction, but if you don't know anything about reduction and its relation to this map, namely it may not be defined over those good reduction. Yeah, sorry, I didn't add any words about this map, but I want to say it's just a map. And then what we have here is that if you start with the local system, over target, the free image of that is also satisfying the same condition. So maybe you don't have to know anything about like any like reduction of this map, how it's related to reduction of whatever models you choose. As long as you get this map of that and the local crystallinity and semi-stability is not preserved on the fullback. So in particular, in a very special case, we just choose like, this to be identity map, and you have different models in mind, and then it's kind of implying that this notion, the crystallinity and semi-stability, is independent of the choice of the smooth or semi-stable models. So this is the first one. The second one is slightly different from the content here. It's more about the deformation theory in a graphic setup. I think classically people call it content injection. So let me first state a statement and then comment on what is really being in deformation. So that is if we start with and that's right.
HVN, we write V modulo NV.
Thank you. There's a saying, no, I finished, right? It's the statement saying that say you pick your very local system and you look at this multi-to n reduction for each n, and turns out you can find some different local system which is crystalline. So that the reduction is equal to the given reduction you have. And it is true for all the n, and then the claim is that the original local system that you start with is also crystalline. So this is
And there's no like uniformly bounded flash take weights type condition.
oh thank you. Yeah, this is of a fixed rate. Yes, thank you so much. Right, this is a statement, and originally it's, I think it's conjectured by Fontaine in 1997, and So this statement looks very abstract. A very happy consequence of this is that like can use this to show very quickly that the locus of crystalline local system, and per deformation space is actually closed locus.
In this theorem and corollary, does X need to be proper or?
No, we don't need any local condition. Sorry, global condition.
Okay.
Any,
Okay.
yeah. What's it called?
In the corollary, I have to say also in with watch state waves in 0h
You mean?
with deformation.
Yeah, we need to fix that. But I think probably it's not normally how you always fix finite amount of cost.
It's close for which topology?
Very simple ones. Like you just locally you pick a certain local deformation ring, and then it's just cut by certain idea.
Bounded watch state please.
Yeah, boundary hospital.
Should really write this in the corollary because otherwise
Oh,
it's really
thank you.
Deformation space.
This is something which I just realized this week. So that's a very quick corollary. And I will also mention a little bit. So this work has recently also shown by Young-Suk Moon. Let me write in. So that's how it's from hand. For fixing local system, this was also shown recently and moved. We use a different approach by considering this problem for p-adic field with improperty relative and together with the purity property of the local system. But here, yeah, I think I read it as theorem, but it's really a kind of corollary which you can prove just by 3 lines. You know already the theorem P3 together with the work of Hong Liu in the case of exercise. Reality. This is proved by just combining work. Or show that if you look at same statement but for p-adic representation of a Galois group of a local field, and then so this statement. So yeah, so that's kind of the statement I want to say, which is kind of some quick application of theorem P3. Are there any questions for that?
So you state this pointwise criterion for crystalline local systems only for things which have smooth models.
Right. But yeah, thanks for asking that. So actually in my article with Chen, we kind of extend this notion, the crystallinity and some stability for all p-adic formal scheme. So it's a notion which you can state for any p-adic formal scheme. But you have to be slightly careful. So I can show that there are, like, if you do something for irregular or not regular integral models, the notion, the crystallinity with respect to those bad models could be different from the smooth models. So that is, if you want certain notion which is kind of totally depend on generic fiber, and then it's kind of require you to put some regularity on the model. Thanks for the question. Okay, so now I can talk a little bit about like what goes into the proof or kind of the tools that we used to get this Pointwise criteria. So if you want to check certain local system, sorry, in a classical case, if you want to check certain Galois representation to be crystalline, so how do you do that? Let's recall the strategy in the case of point. Let me say first class. So in this compound, you start with a representation of Galois group, and you want to show that this representation is crystalline. The way you do it is that the first step is to show this representation is actually the one. And by what we know, what the round representation in a classical sense, and so it in particular implies that it is potentially semi-stable. In a concrete sense, that means you can find finite extension of p-adic field, and so that is totally quantified. And for convenience, let's also assume it's Galois. Other restriction. But once you know that this representation is semi-stable up to a finite extension, and then to show that the original representation is semi-stable or even crystalline, it's suffice to understand the so-called DST module, or decreased module. So the setup tells you that there is a finite group action on a modular, which we write a DST of very specific to our data point. So this group is a finite group, and this DST, the finite dimensional vector space over K naught, carries the four Venus modular and monotony actions. Over K naught, or by definition means like fixed ring over radicals and uniformity. So it's a very simple linear algebra data. And then, let me just finish. You have this finite group action, and then to show the original representation is semi-stable, and then it's fine to show this action is straight. Let me call it group G. Action is straight. And for crystallinity, you want to show additional condition that this monogamy acts in the general map. Okay, so this is the case of point. Namely, if you want to show some representation to be crystalline, this is what you do. Now we want to kind of carry this strategy to the relative setting. But you notice like there are some things you need to check. What kind of first establish before you can talk about those notions on board. So the first thing is that like you want to be able to use the crystalline assumption on points to say something about the Riemann representation or the Riemann local system. So this is something which can be shown quite quickly for some rigidity theorem of Riemann Guo. For the second part, you notice that you want something about the action on certain Fourier modelers. And so this requires this existence of DSP for a local system. So that it's kind of functorial with respect to the local system that you start with. So in particular, you want in a rectangle setup, you want to have certain act as a crystalline spiral fiber so that it's functorial enough with respect to the data you speak. This suggests that you probably to first consider if you can extend this DSP functor to a quadratic setup. So in p-adic Hall theory, the first step is this Riemann notion can actually be formulated quite easily using the Riemann functor. And in a rectangle setup, this was actually carried by Riemann Guo. This in particular is a critical input for showing the rigidity theorem. So if you want to finish an entire program there, you want whatever functor you can trust for the DSP in the rectangle setup, you also want it to be compatible with Riemann. And then, so how do you do that? So one of the more theoretical contribution of our work is that turns out we can actually find such a functor in our setup here. And so we recall that in the U2 setup, like the p-adic is a functor from local system functional fibers with filter connecting into that fiber. So if you want to refine these things, you have to first ask what should be a correct target category so that it can capture things happening on the spiral fiber. So to talk about like the construction or in particular varied leaves, and then we introduce this notion called HF as a grid. Let's say. There you can start with a scheme for the G. And then you can have so-called the big grid. There's a functor such as extending any open subscheme in this way when F as a crystal over it. carry the condition that when you're restricting this f as a crystal from bigger open to a smaller open, let's say the restriction here, where is the canonical injection of f as a crystal from larger than smaller. Sorry, from one divided on a larger open to smaller. So this can produce a category that's denoted as W of n, let's see. And then this category contains the original or more classical notion about as a crystal as a full subtype. But what is interesting about this larger one is that you can kind of the rank of f as a crystal can be changing when you restrict to from bigger subspace to smaller ones. And so in particular, you can have some example which is a large streak functor. You have open inversion. So what you get here will be a certain characteristic shape of as a crystal, so that if you restrict to certain open, which is not within V, and then you get there. Now I can state this the enhancement of the Riemann functor, which we call it as a crystalline Riemann Hilbert functor. So say you pick your favorite p-adic formal scheme that is smooth. And then what we produce here is a diagram of functors. You start with local system on standard fiber. And now what you get here is that you have two arrows. For the first one on top is that you take this straight cap as a crystal of a spiral fiber. But you add an additional data which is called the nilpotent endomorphism, the capital N. And below you just look at this category of a straight cap. And in the vertical arrow, so since you have an endomorphism on certain as a crystal, you can look at this kernel of this endomorphism. The top one we call it ESP. The lower one we call it decryption. So kind of unite of a DSP and decryption in a classical setup. So this is a functor we construct, and then what properties do you have here? The first one is about what can you say about image or size of that? It's called rank condition. That is, if you look at the rank of ESP, so as we mentioned, the ESP here, target category is a big F as a crystal. So in particular, when you're talking about the rank functions, there should be a certain function on this entire characteristic size. The inclusion conditions is telling you that while kind of shrinking from larger open to smaller open, the rank will only go up. So in particular, you get kind of bounded amount of, well, like you can get a chain of integers. And then what we say here is that this rank is bounded by the rank of original local system that it starts. And yeah, I mean, make it as a inequality. So these rank functions are non-negative functions on the other side that is bounded by I think image we usually denote it as increase t and e as t. So you got this kind of boundedness. And moreover, like in a very, very special case, when you know the rank function is actually constant, which implies that this recap as a crystal is actually acts as a crystal. And we can actually say something good in a sense that it gave you a criterion of a crystallinity and stuff like that. So B is decreased or semi-stable if the rank function is constant. Sorry, because it's just equal to a constant. System. Same way. So the first condition. The second condition is about pullback. So this is called the pullback injectivity. So if you have seen like this new article about p-adic Riemann Hilbert, you will notice that the most important property for their functor is about this pullback conditions for the given one. So that is, the rigidity theorem is really follows from this fact that the d-derived functor give you as a morphism whenever kind of pullback to a different p-adic rigid space. But what happens in this sometimes the more refined notion for crystalline or semi-stable local system is that this will never happen in general. But instead, you got some injectivity, which is not so bad. That is for map of p-adic forms T. And then there are natural injections, which is saying first take pullback. Say you look at it, please. And this will inject into, you look at the image of Riemann Hilbert, but at the pre-image local system. So once you have this pullback injectivity, you can ask, so when does this injection become isomorphism? And this is what we call the smooth space change theorem. Which is saying that this happens if your map is actually completely smooth. So that is, if I call this map to be outgrid. Sorry, I forgot to say this is not possible, I guess. The first condition is about compatibility with the more classical p-adic Riemann Hilbert. So what this really means that so the equals or EST is kind of certain constructions for a special fiber. But there is a way to kind of evaluate this as a crystal or weak as a crystal so that you can get the shape with a connection structure on the generic fiber. Roughly speaking, so say you have as a crystal special fiber, and then you can look at the following divided power secant, which is just given by choose the p-adic formal spin that you start with, carry a small q reduction. So this pair is a PD thickening for a crystalline site of a multi-locus. So in particular, it makes sense to consider the evaluation of certain isocrystal the thickness. The outcome will just become certain shape on the generic fiber of X. And what we have here is that this naturally sit inside of the d to the functor of U and 2. That is compatible with the connection structure. So that's also kind of the reason why we call it the Kristen Riemann Hilbert. Because this is how they call it. They call it the Riemann Hilbert here. The last condition is that this functor is actually like kind of refines or extends original equation is SP functor to higher dimension. So that is, although it's kind of formulated in different language, but in the case of point, it really has no difference with classical. Oh, sorry, I ran out of time. So I have to stop it here. Sorry.
Questions?
Yeah, okay, great. And so like in Luchu, this like, DR is factored through like the other like functor that goes to generic fiber, like vector bundles potential on sort of the B to ROM, the base shapes of B to ROM with the original variety.
Right.
Does such a thing? Is there such a factorization in this crystalline case as well?
The question is, the original you do a speed around functor as an enhancement where the target category is vector bundle with connection over the speed around linear structure shape. And we have this kind of enhancement for equation ESD as well. And my guess is yes, but somehow, yeah, I think so. So what I have in mind is that you want certain modulars over a structure shape completely tangled with different ring, for example. And if you're thinking about what is this ring, and this roughly saying that you first take T-complete tensor product with this aqueous, and then do some localization. But if you think about this object, it actually can produce a PD thickening of the special fiber as well. So it makes sense to evaluate this as a crystal and just such a PD thickening, get models from that. And so yeah, my guess is yes, although I didn't really work out the details.
Yeah, maybe you already said that, but when you take this semi-stable, I mean, sorry, do you actually prove that have a definition of semi-stable coefficients just for rigid analytic varieties?
Yeah.
Yes.
So, yeah, right. You can talk about the semi-stability of a local system with respect to any p-adic form-free models that we choose or given really space.
Oh no, but I don't have a model. I mean, okay, I have a model.
Yeah,
No, but I don't.
yeah,
Sorry,
sorry.
I don't have a model.
Yeah, I guess your point. So as I mentioned previously, so that is people choose semi-stable models. Whatever model you choose, turns out a posteriori the semi-stability with regard to those models are all equivalent to each other. The consequence of this. So, but people choose different models which are even worse, and then the semi-stability could be actually different from.
No, I understand that. But now, once you have this semi-stable, good theoretical semi-stable models, now we can do descent, right? On the attack descent on the generic fibers. You can do these things.
Yeah, well, this is something I really hope to understand better, but somehow there are some subtlety about descent things. So, roughly speaking, whenever you want to descend to get certain f as a crystal over a given special fiber you choose, this hypercover you choose has to be a hypercover in the entire input level, not just over generic fiber.
But why? I mean,
you're conditioned about. Yeah, it isn't. I mean, you're conditioned about sort of true at all classical point. I mean, isn't that sort of automatically?
Yeah, well, that gives you a bad notion of that, but I hope to kind of understand this notion for all possible models, and that will be fine. But yeah, if you just choose, or if you just with respect to good models, and then this pointwise condition gave you a good notion of why semester local system.
Sorry, I was asking something else.
Sorry.
So you have semester local systems, and then you have equivalent, I mean, you have a model, you have an equivalence with certain category of any crystals, logarithmic stuff like that. And so I want to define this category on this side, so to speak, only on the generic file on the regional on the region. So what is the equivalent category to the?
I see. So this also, yeah. So in a good reduction case, you can use this August notion about converting the F as a crystal, which is formulated as a certain flat connection over generic fiber, together with the additional action by some group. And this can.
And this can you group that?
Yeah, you can group that. It's a global.
For rigid space.
Right. It's defined totally for any p-adic formula scheme on this generic fiber. And this.
So that gives you an equivalence.
You can get this kind of formulation.
I wanted to ask about so you mentioned this, you described the strategy in the absolute setting. But so what is how does the strategy look in the relative? How does the strategy
Yeah, exactly. So it's kind of you're asking how do I prove the theorem?
Yeah, so using everything set up, how do you prove it?
Yeah. So it will take me 5 minutes, but I can try.
Shorter version.
Yeah. Okay. I'm waiting like 2 minutes.
I can ask you. I can get a longer version.
Right.
2 minutes.
Okay. The quick way is first to realize that the assumption is that this local system is pointwise crystal, right? So it implies that this is the Riemann local system by rigid. All these are even restricted things to a so-called zero point rigid space. We can think about this kind of point is a kind of certain rigid analytic scenario point. Or it's L zero. Here I think X has good value. So once you have this, and then it's a kind of result in p-adic Hodge for imperfect for EVR with imperfect variability, which is saying that there's a finite extension of discrete variation ring, such that the restriction of this representation is actually some thing. So here L and L prime are P-complete radiation field, but the radio field is actually imperfect. And the question now is kind of how do we extend this semi-stability on the generic point through entire p-adic formal scheme? And then so what we figure out is that once you have this finite extension up to requirement, you can actually get the power of the finite coverage of p-adic formal scheme. It's a message, sorry. I'm saying we have a finite power of p-adic formal scheme, where the components of those map are given by something which you can understand quite easily. The first one is the extension of phase ring, running by the extension of phase ring. The second one here, let me say this. It's certain P completely involved. And then the later ones are given by so-called the inseparable extension, or we call it primitive inseparable extension. Which is the finite cover of p-adic formal scheme, such that on a special fiber is purely inseparable but on the generic fiber, it's a degree P Galois extension. And then, so the rest of the task is to kind of notice that this semi-stability of this restriction can actually tell you the original local system once restricted to the last color is actually a set of local system. Let me finish the sentence. That's fine. I'll try. Yeah, so this is so-called purity result, which recently established by Wu Liu, Moon, Schmidu. That is this local system V, once you restrict to this color, is semi-stable. And then the rest of the task is to show that for those standard morphisms, if you know the things, the crystallinity or semi-stability on the previous one, you can actually show that the original assumption about pointwise, you make it actually descend to the level below. And that's it.
It's a, yeah, again, maybe I'll have some follow-up.
Yeah.
But we should.
Apologize for not making it short.